Hello, everyone. My name is Filippo Utro. I'm talking about here from IBM Research in New York. And I'm going to talk about some of the research and application that we have been recently doing in healthcare and life science. I'm going to talk about, indeed, the two tracks, the two main area of research we are doing right now. One is in the AI space. The other one is the quantum space. But both of these two have a sign is to provide impact in science. We want to provide an impact, but those impacts have to be, we want to be high. Usually those are also being recognized for the scientific community through high real impact journal paper. But we realized that we cannot go and do high impact alone. We cannot be just on our own. What we can do only is to collaborate with community, create strong partnership with other institutions, both in industry, so pharma, academia, or in healthcare space, such as Cleveland Clinic, Mount Sinai. Some of them are listed here, but it's not just an exhaustive list. Those are just a full example of those. And one of the latest examples that actually cover both of our tracks is our recent collaboration with Cleveland Clinic. So we decided to create a strong partnership with Cleveland Clinic in the world of healthcare and life science, where we plan to accelerate our discovery in the world of medical engineering. So define new possible target, help in clinical trial, develop a new possible biomarker, new molecules, new drug, improve the fast and the speed of drug development. And we recently developed these are partnership, as I say, it covers both the AI and the quantum space. So what you see there in the picture, close what it looks like a beautiful cafeteria, which actually is a cafeteria. You get an actual quantum computer there. You see there is the quantum computer that is the system one, which is now available in Cleveland Clinic. Since then, also, we expanded our collaboration. There are more quantum computers available around the world through our partner there. There is one in Quebec, one in South Korea, a new system two in Troy. There is one also that's going to be built later on in Japan. We have also in Germany, Spain, and so on that are also being constructed too. So let's go directly one of the first two things. Let's start with the AI one, and then I'm going to move on to the quantum side. And just a brief story of AI, I'm pretty sure everyone knows that we started and then there was the boom of AI, which was in the late 2010 with the notion of machine learning, the SVM, the random forest, and so on, where we actually found useful application for those elements. Later on, we expanded those to task-specific with deep learning, and now recently we have the new era of foundation models. And of course, there is a major difference between what we were thinking as traditional machine learning versus the foundation model, where in traditional machine learning, you have a very specific question on a very specific data set. You are taking your model, training on those, and try to answer your task. Try to complete your task and target on that. That model, though, was not very general. You cannot apply anyone else. It was very tied to what he was learning and see at that time. And then it was going to take a bunch of time to see a new data, trying to improve your model and getting done too. The new paradigm, which is the one of foundation model, instead is given a bunch of data, which not necessarily have been labeled, is trying to mimic what the human brain is going through, try to learn by seeing stuff, not necessarily that those are labeled to. And then you can fine-tune those models in a specific task that you want to, and a specific question that you get through. Of course, these are specific challenges, as well also new opportunities, which you can get through. We start them from the first generation modality. Now we have multimodality. We can also have the notion of explainability, which was lacking, which is now becoming also a benefit that we're going through. And of course, there is adoption and so on. In the world of biomedical side, of course, what you see, for instance, or better to say, what is being added to you right now from the text there is the development of new target. And what is laid on top is somehow a workflow or a biomedical foundation model. It's not a perfect one-to-one map, but actually you can map that framework in several points of the drug development phase. And you start from a series of data. It can be a single modality or multimodality in the ideal case. and you try to do an early fusion, model fusion, you apply foundation model, and you do fine-tuning of those models, and you try to adapt that information to a multi-task such that will lead to scientific discovery. Now, recently, on top of that, you also have the notion of agentic workflow, which you can integrate those flow with new insight or specific questions that you get through. So as I said before, in the notion of biomedical foundation model for drug discovery, we cannot do this on our own. Those are listed some of our partners too, and some of the usual modalities and workflow that the foundation models do. And what we want to do indeed with our partner is to create new foundation model, discover novel target, novel elements in the biological or small molecule, and we want to validate with them, either in silico or in vitro, to help validate our model and see the benefit our model goes through, right? And then what we did then was develop some 4 models at the moment. Those are listed there. You can find the link of the paper there. I'm not going to go in the details of each of them. Please feel free to contact me, see me or any of my colleagues that are around from IBM and ask questions about those models. The paper are online, they're public available. We also provide the model itself on Hugging Face. The link for Hugging Face you can also find in the publication itself. And the first model, for instance, is around the molecule view, so which we call MELON, is a multi-view for molecular design for small molecule. We actually, there, MELON use 3 main sources of information: the actual imaging of a molecule, if it's available, the SMILE sequence, or the graph representation of the molecule itself. We try to combine those 3 to predict new molecule there. Another one, which is what we call MALMAL, is actually a multimodal approach, which we try to use a T5 architecture. And the last 2 are a biomedical foundation model for RNA or DNA you get through. So you can see there how the different model, it's not properly viewed, but you can see how MELON is very specific for small molecule, using different kind of structure of the architecture. You can get MAMMAL, which is a multi-view or multi-modality, and then you get very too specific with the other 2 foundation model. And on the right, you can see some of the data, public data, which they've been training to. Now, as I mentioned before, and as you were aware, from foundation model, the new thing is also agent, or now becoming the multi-agent aspect out of it, which also can be integrated to a foundation model with some specific question that wants from the user, from the scientist part, from the researcher, a specific answer to. So for instance, we want to filter some antibody candidates, and the question could be, given my peptide of interest, could be able to determine what are the following antibody to. And then given this agent, the workflow will work with the foundation model to answer those. And what I also want to emphasize in my talk is that this, in IBM Research, we're developing those tools, but we want to work with you people. We want to work with the community. We want to build a trusting community that use both AI and quantum. So what we did then was also to begin to be part of an alliance in AI, which covered different aspects. One of them, of course, is also drug discovery. So we created a working group. There was a first version that was last year in October in MIT in Boston. And this year is going to be a virtual event. Please feel free to register if you're interested. That's going to join the event, be part of the discussion if you're interested going to. Hopefully you can scan the QR code when the thing goes away. Or if not, please let me know. I can try to get you the link to get through that. Other option to validate this in community, if you have been seen here yesterday, we are also part of the Dream Challenge. We are very focused also in this public effort, in this crowdfunded resource. Yesterday there was a great meeting and part of the session here at ISMB. For the few lucky of you, they were able to go in the room. And it was very crowded too. But those are some of the effort we are trying to get and use the community. We have worked with the community to help and move on to our discovery, to provide high impact discovery to them. So for instance, let me show you some results we've been done with one of our partners, which is again Cleveland Clinic there. So the first one is And you can see for all of them, there are public scientific papers which are available, which you can go connect to. I'm going to just give you an highlights of this one, where we use our foundation model to high fidelity primary human cell culture with our foundation model, and we can see a high concordance between the in vitro and the in vivo representation of the transcriptome of the cell. Between those two, you can see those in the two graph over there. Another example is the drug repurposing for Alzheimer's disease. This is also the paper that you can get and see more details there. We also apply our small compound models, and those of them can also be done, for instance, using for influenza that we get that. These are all publications. I don't want to, for sake of time, go in each of details, but if you have questions on those or any application for our foundation model, please reach to us, okay? Now, I want to switch gear and go to what I call the future of life science, which is actually the present. It is in quantum computing too. So IBM has a long history in quantum computing. What you see here is just a quick timeline. On the top, you can see how they're marked there, some few of the milestones on quantum computing. And on the top is one done by the scientific community, IBM. You can see how much IBM has contributed to the quantum computing during the history of time, and how much also we are going to contribute in the future, in the near future there. Indeed, we come up with our own roadmap to actually provide and improve the world of quantum computing. With this roadmap, which is quite confusing at the beginning, so let me try to navigate there. You actually have multiple levels of our roadmap. The first level is on hardware, because we want to build better and faster quantum computer, less noise. Indeed, we plan to have, by 2029, a first fault-tolerant computer with 200 fault-tolerant logic qubit. And the other level is just, okay, we have a quantum computing, we have the hardware, what we do with that, right? So we want to build the software, better software to work and build new algorithms. We want to build new functionality, and we want to find application for those quantum computing and those applications. Doesn't mean that all the application in the world is going to be solved by quantum computing. There may be very specific application where quantum computing will be needed alone, or there will be application where a quantum computer can work with the classical computing to find a better solution that otherwise will not be feasible to. So as I said, we start working on the application side, and we first thought about the using of single cell data where quantum can go and provide some benefit to. We identify 4 possible problems where this could be. One is in a low data regime setting. This, for instance, in the case of immunotherapy. So you have a small amount of data when you want to decide better CAR T therapy. The other one is in the notion of modeling the microenvironment tumor perturbation. And the bottom, what you see on the bottom, is actually to identify hidden pattern discovery in your data too. So we're going to quickly talk and show a bit of them, some of them. In the case of immunotherapy, there you work a very small amount of limited sample, where classical models, they are not general enough. They usually overfit because we're talking to a few hundred data points, which creating more is very difficult, and sometimes you don't have the time to create in those. So there is where quantum can go and provide a benefit. I'm going to show a bit more later about the microenvironment. The tumor perturbation, there are several ways. For instance, the most standard right now is also considered optimal transport. And there could be components during the optimal transport process where quantum computer can go and provide a benefit too. All of this is around the notion of cell-centric therapeutic. And with our collaborator, we decided to put some effort, and we write a prospective paper, which is right now under review there, but it's also available right now in archive. If you're interested to, please take a look. And I also want to mention that not for all problem, there is a single solution to that. For each specific task, there could be specific approach that could be applied to. Some of them can be in the near-term quantum computing. Some of them we need to go along need more fault-tolerant approach. But we know the door exists. We want to keep in our eye such that we can work and be ready from the quantum, from the hardware is going to be there. And each of them might go back to a specific biological question you want to go through. As I say, we want to build a community. So we actually create a series of working groups around healthcare and life science, where with collaborators, not necessarily just Cleveland clinics, but all around the world, we try to get a specific question and problem where quantum can go and provide some benefit or can be a support to a solution and to a specific application. And if you are interested, if you think you have a specific problem and you want to join our effort, please let me know anytime. We can try to work together. We can try to create a working group. We're going to meet once a month, once 2 weeks, depending on your schedule and so on, and try to come up with together a solution. But we want your problem. We want your expertise about that problem such that we can actually go that and get you. One example, for instance, is in the role of biomarker 2, where this is paper that was recently published in Cell Pattern, again, was focused on see where quantum can be beneficial for discover new biomarker too. Of course, when you discover biomarker, there are different data modalities that you can consider too. That is what they're listed here on the bottom. They could be electronic health record, they could be omics, they could be images. And each of these modality, you actually have several nuances too. That each of these nuances can also create specific problem, and those specific technique you need to start to consider to actually answer those. We try to align them in this very high-level points figure two, sorry, where of course you start with the pre-processing. There is some specific kind of quantum algorithm that can be helpful for that. Of course, in some case, there is a classical quantum part, but then there are specific limitations on the classical side, which cannot be, can be tried to be solved by the quantum one.
Sorry, I have to check the transmission. Sorry.
And there is some water in the meantime.
I don't know. Stop the transmission. I don't know.
What's going on?
It always was working.
It's fine. Yeah, it's still on.
But I am receiving this message.
They're in the wrong room.
Is that the same one?
Oh, I get this. You're good. Go ahead.
Okay. Please, sir, you can continue. Thank you.
Yeah, I don't see. We'll just put a slide back here.
Sorry.
Okay, let's resume. So yeah, there is some specific application and specific use case application where quantum can go and provide a benefit. One of them that we were thinking when we were writing this paper, which we are actually working on right now, is the analysis of longitudinal data. For instance, one of the problems of longitudinal data in the biomedical world is that often those data are sparse. You may have few patients that you follow around some certain time, and not all of them, they are getting points at the same time. So you might get one patient 2-3 time points, one you might get 9, and those time points may not be perfectly aligned to. In particular, if you can think about a clinical trial or in cancer therapy, you might also have a different response of the patients, which it might come more often to the clinic, so that you get more time points or less. And also as a previous historical background, you might lead a different answer too. So the analysis of longitudinal data in classical is very difficult. Usually mostly is being done through observation and combinatorial analysis in some case, such as, for instance, tumor heterogeneity. But you will see a single patient analysis too, and then trying to do some meta-analysis on top of that. While here we're trying to analyze all of the data together and see if quantum can go provide new insight about the data. In this recent paper that we posted in archive, which we are working on also to further this, we were analyzing 2 different diseases and 2 different data modalities. One was RNA from follicular cancer. The other one was basically a signal from, I believe it was Alzheimer's, that we're actually getting through and try to classify the data and possibly predict the response of the patient through the longitudinal analysis that we go through. Another area of interest for us is also in the role of network medicine, which you may have a graph, And there are techniques in the network medicine such as random walk. And there is, of course, this quantum counterpart, which is nicely called quantum random walk, which actually is being shown to see different aspect of the graph that the classical is limited on what the neighbor of the node are. We're going to have actually a talk today. The paper is also online. The link is on archive. And Aritra is going to give a talk later today at 5 p.m., which was the info highlighted there, which is nicely hidden to you. But please check the schedule for the room and see it's later today at 5. Okay? Another analysis we're also considering is actually in the world of quantum ensemble machine learning. So you don't have to necessarily give a single model. You might have multiple models. Those can be all classical, and then you have a quantum component to pick up how you ensemble those. You can have quantum machine learning and classical machine learning and then analyzing them together. This is a paper that we recently put through, also considering a full quantum cosine classifier too, that help us to provide analysis of a small cohort of renal cell cancer, and with as well not just simulated results, but also other results on around 56 qubit that we were able to execute and see some benefit out of it with respect to the classical machine learning and the classical experiment we ran through. As I say, we're also interested in the analysis of microenvironment of the tumor. So there are also a few quantum opportunities there. For instance, in classical computation, when you perform the embedding, the data can be very not separable. When you move them to a quantum space, those separation of the data can actually be happen to. So that's something that we're analyzing. We had a paper that was recently accepted and published last year in a quantum computing conference in 2024. The paper is available there through the QR code. Nicely, this time is on top, so it's not be hidden. So you can actually see the paper if you're interested too. And the idea there was actually providing an hybrid approach that used the embedding of a graph neural network and a quantum machine learning, which in this loop between the two, such that you can perform a better classification of the tumor cell. As I mentioned before, there is also some very combinatorial explosion problem which quantum can go and solve and classically is not amenable to. Thinking about the population analysis when you have multiple confounding factor of a disease. So you always start thinking, I want to analyze HR data, I want to analyze multimodality data, or even a single modality. You cannot go beyond 2 or 3 feature analysis, 2 or 3 way interactions, thinking about epistasis that could lead to extra comorbidity of the data. Think about, for instance, in neurodegenerative disease, you may have inflammation, which is an outcome of that neurodegenerative disease, or a multiple aspect of them. For instance, if you have ulcerative colitis, IBD, you might end up being as well inflammation, but with some brain possible disorder. So you have this confounding factor coming from different disease, and finding those in high level of interaction in your data is very combinatorial difficult because it's a large explosion of data. There is like a cumulant analysis, both at population level or a single level, which you can again retransmit that in a single cell where you have multiple cells interacting to each other with gene and so on, can get through. And then their quantum can go and provide to solve and navigate the combinatorial space to get a new insight and find hidden pattern in the data. That's some work in progress we're going right now. Hopefully we're going to finish the paper in the next couple of months and post it in archive. So if you're interested, please stay focused and let us know. One more recently also work we've been doing too is also make these tools, new functionality available to the community. So not only you have Qiskit, which is the largest Python-based tool for quantum development, but also we make more abstract elements for practitioner in the life science aspect. So we create QBioCode, which is recently being pushed as open source. It's a community aspect, it's a collaborative environment for life science, where we provide a series of API of analysis of your data through quantum machine learning and quantum computing too. So there you can, through API, you can develop new tools. There we have listed a couple of them that we have been developing recently, just as a few examples. Those are Profiler, which will allow to profile your data through classical quantum machine learning, and Sage, that will allow, given the data characteristic of your data, not even your data itself, just the characteristic which you can compute through Profiler, will tell you more or less which model is most suited for that. And we're also going to have a poster around this approach, believe today as well, not tomorrow. Yes, so tomorrow, please find us. We can talk and chat more about it. And as you may guess, we also have a lot of talks around different aspects, both AI and quantum. The QR code lists to all our talks here in ISMB. Please feel free to find us, ask us questions. And if you have a problem which you think one of the two aspects, either AI or quantum, can go and solve, we want to collaborate with us, please reach to us, okay? I will happy to take question right now.
Thank you very much for a fascinating talk. Are there any questions from the audience? Probably quite a few. There's one online as well, so in fact, there's probably two online. Who is first?
Thanks for presentation. And do you have any comparison between the classical methods, hybrid methods, and pure quantum methods?
Yes. So when we define a new, first of all, when you define to work on a problem, we want that problem to be difficult for the classical side. We want problems that are not tractable or where classical usually fail to. But when we define a new quantum algorithm, we want to also justify that actually quantum provide new insight, new element bring it to the table. So we not just compare that quantum algorithm with maybe its classical counterpart. So for instance, imagine if you have a QSVM, we not just compare with SVM, but we compare with the best state of the art. So we always do that to justify and see, okay, it makes sense to do these experiments. It makes sense to do it. We actually provide new insight. We provide new benefit. And this new insight, actually, I also want to say that it might not be as fast as classical in some case. It might not be, in my case, it might be more precise. In other case, the two of them can also work together. So the quantum can provide insight about your data that the classical is not helping you to, and vice versa. And then, for instance, is some of what we're going to talk later today with the quantum random walk, where actually the quantum random walk is seeing the graph completely orthogonal view of the classical, providing new insight about some neurodegenerative disease.
Thank you for the great talk. I have two questions. One related to the AI part. So we have shown several large foundation models. I wonder if you have considered multimodality large foundation models, or
yes, so
explore this.
We do have MAMMA, which is a multimodal large foundation model there, and the paper is online on arXiv, as well as the model is available on Hugging Face. And we also compare MAMMA with also state of the art there in the paper, and then we also consider that too.
All right, good. So the second question is, I think you probably already touched on it, but what quantum computing excel at, just in terms of problems in general?
Okay, at the moment, we think there are few fields where quantum computing can go and provide its first advantage to. They can be, for instance, a more established study as quantum chemistry. Other case can also be seen in optimization, where quantum computer we expect to see the best.
How do you access the quantum computing?
There are different ways through partnership or to system. There are quantum computer available. We are not just also the single provider. Let me also say that. There is a question there and then one there.
In terms of so we know what pre-processing looks like for the AI component. What does it the same for quantum, or it's different, less emphasis on having clean data? What's the input?
Email is domain and problem specific too. For instance, in some case, if the nature of the data is small and it fits, it can go. There is no need of pre-processing at all. by also sometimes provide some pre-processing, also help you to the interpretability of the data. You know that some pre-processing on the data is given to you. For instance, imagine you have RNA, you always do a standard scaling, you'd also do you do this first step, is always been required to, and that's also where the domain expertise come from, to actually do a pre-processing of the data. Then there is a quantum-specific pre-processing, which is move the classical data to the quantum space, but that's an extra step you need to do it in some case.
Okay, just maybe just a couple of questions online because these came out first. First from Edgardo Ferran. It's a related question to one you've just answered, but how should we select the right applications for quantum computing, and why quantum computing would be better than standard computing for certain applications?
Okay, how you select? Usually you're trying to find problem where classically you have all try your method and classical do not work. You have like a bottleneck in your data. You can see that the no model, for instance, if you're thinking about a prediction task or so, or you know that there are specific limits. Think about in case of quantum chemistry, you know that there are specific limitations on timing and the capability of the computing to predict a certain level of energy, where actually quantum can go and do that aspect too. So that's, for instance, the case. Usually quantum considered is it's like you have an elephant in the room and you want to move that elephant to such that you find the right application. You want to be sure that it's the right task. So you want to cross your T and dot your I that I try everything else and it doesn't work and I want to do it. And then also the question now, you have to think, is my problem a right problem? Can I fit my problem in the quantum space? Is actually the right solution to it? But somehow it's also what you do in the classical space. And you say, oh, is a transformer the right approach, or maybe a random forest will still solve it, right? So it's the same analogy you may have there.
Okay, thank you. Just a second question. Edgardo says, thank you. Nice talk. So another question from Daniela Gao. Thank you for the talk. Can you explain why we can't currently run analyses on quantum computers for large data sets? And can you explain if this is a physical constraint of quantum computing, or is it a matter of the hardware size?
Mainly, yes, it's a matter of mostly of the hardware size. Indeed, as soon the hardware gets better and larger, you can run more sample and more feature into it. Again, we're expecting to be increasing to 1,000 of qubits in the next couple of years with better quality as well.
Just a couple of questions, if you'll indulge me. So what is the scaling law for number of qubits, right? So if you are increasing, you said we would have a quantum computer for 200 qubits. What does 1,000 qubits get you? Is it the same as GPU cores or CPU?
No, it's not the same. First of all, let me say that we're going to have, in 2029, we're going to have 200 fault-tolerant qubit. Actually, at that tier, the same machine might have like, I think, 1,000 of qubits already. We are ready in the regime. You think about it, the hardware is moving at a speed which is incredible too, because we were working with 8 qubit, let's say a few years ago, say 3 or 4 years ago. We are now machines which are in the 127, 130 qubits, with also better quality of the qubit itself.
So that's my question. So what?
It allows to run larger problems. Let me put
Okay.
in a simple way. In a simple way, you can see that. It can also do many more things, but in simplistic, you can see that.
Yeah. So the question is it concurrency that you get with more qubits, or is it bigger problems that you can solve with qubits?
Can you repeat your question? Sorry.
So for example, I'm thinking from a traditional point of view, which is CPUs and GPUs, right?
Uh-huh.
The more cores you add, you get more concurrency into your computer.
No, you can. There is like system 2, which is like you can also think about like this. We have multiple QPU talking to each other as well. There is a silicon integration between QPU and GPU. But you also get larger problem that you can run in each of them. That's what you're expecting with increasing number of qubits.
Oh, see. Okay. So my main thrust of the question, because there's a lack of quantum computers in the world, which researchers don't have access to, would it be worthwhile for companies like yourselves or others to create a quantum simulator, a quantum computer?
These exist.
Oh,
We did, yes, we
so,
did it.
so could we test out that
So
algorithms on that simulator first before
yes,
we get
that's what actually is the usual workflow. As I say, Qiskit as a standalone is actually the largest toolkit for quantum computing programming too. It's Python based, so it's also based using the same sklearn framework style, so it's very easy to use, and also comes with different simulator approach. And you can simulate up to 20 qubits, for instance, too, which is the usual approach before, even our case, that we might have access to a quantum hardware. We don't want to use the hardware directly for any proof of concept. We have a proof of concept simulator. We run a simulator. We see what we're expecting to see in the small problem, and then we scale up to actual random hardware.
right? So yeah, it would be really useful to have that detail of the simulator because that
It's open source. Okay. The thing is, Qiskit is open source. It's available to everyone, and you can access to it.
I just have a related question on the cost. I mean, the cost is very high. Is this really prohibitory for certain
No.
questions because of these simulators that you have? I mean, how do you see that going forward in terms of the cost of quantum computing compared to traditional computing?
I mean, the cost. You think about how much it costs to keep a server or GPU. More or less, you're there.
Okay, so
you can get there. So it's not the problem. And again, also there are through partnership institution. If we think the problem is solvent too, we get access to it and see if there is also that's also part of the collaboration, right? And the open science community.
Okay, just maybe one question, another one from Daniela Gao. How large of a data set can you analyze with a 20 qubit simulator?
100 samples, it's easy. It's not. It mainly depends on the algorithm you're using too. That's the tricky part. There is no straightforward. If you want to, you can think of 100 samples. You can also do that. Even 1,000. Depends for how long you want to wait.
Okay, thank you. We have just time for maybe one or two more questions if there is one. Otherwise, we can finish. Okay, well, thank you very much, Philly, for a great talk. Thank you, and thank you everyone in the